The function I'm going to choose, a possible solution, one of the possible solutions, even more specific than that, would just be a sinusoidal wave, a sine function. Now, why do people like sine functions or cosine functions? Well, first of all, they're simple to work with, simpler. And the other thing is, in addition to that, or even better than that, you can express more complicated functions in terms of sines and cosines. Okay? Anybody had differential equations last semester at some point? Okay. How did you use, or have you used sines and cosines to express other functions? What was that called? What kind of series? Fourier series. Yeah. Yeah. So yeah, use them. If you're in difficult this semester, you would do it. We're not going to, but just be aware that's why we use sines and cosines. They're simple and they're useful, and you can express more complicated functions in those terms. So we're going to take a specific function. So we're going to say this: e of x and t is equal to j hat, and then some e naught sine of kx minus omega times t. And then b will equal b of x and t is k hat b naught. This is the amplitude of the maximum magnetic field can be sine of kx minus omega times t. Because in a moment, well, maybe next time, we will have this wave that's traveling, and whenever you have electric and magnetic fields, you will have energy associated with them, the energy density that we discussed in the previous class, which I remind you of. So you have energy traveling, and we want to know how much energy is traveling, and then it will have momentum and so on. So that's what we're getting to. Hopefully we'll finish it by next lecture, all of it. So that's that. So I would like to know if there is a relationship between these, right? Between E naught and B naught. That's what I want to figure. So to figure that out, I'm going to use this equation or this equation. So one of these. Let's use this one. The curl of E. Let's figure out what the curl of E is. So we know that the curl of E is equal to minus dB dt, right? That's by Faraday's law. The curl of E. What is the curl? We haven't explicitly calculated the curl, but let's do it. The curl of E the curl looks like this. And then cross product with E, right? But what's E? E is this. It has a j hat component, and then E naught on the right hand side, I have minus dB dt. Derivative with respect to t for b will give me a minus omega out, right? Minus omega out. And then, but there is a minus sign waiting, so it makes it plus. So you would just have k hat omega, and then b naught cosine of kx minus omega times t. I know this lecture is a little dry, but the fun part is we're going to clear this out. And then, it would be probably less dry next time. Let's look here. So first of all, let's look at this curl, this cross product. So first of all, if two vectors, they are parallel, their cross product is 0, meaning j hat crossed with j hat is 0. Okay, j hat cross j hat, so that goes away. K hat crossed with j hat is not 0. However, the derivative with respect to z of this function is 0, right? So So this one and this one do not contribute anything. Next thing is, what is I hat crossed with J hat? K hat. I hat crossed with J hat is K hat, right? By the right hand. So that gives a K hat. Next is the derivative. The ddx of this, when you take the derivative with respect to x, a K comes out, and this becomes a cosine. So we get K E naught cosine of kx minus omega times t equals to k hat, and then omega d naught cosine of kx minus omega times t, right? So what we take from this, the cosine is the same, the k hat is the same, so we notice that these must be equal, right? These must be equal. That means we have E naught times k is equal to omega times b naught. So E naught will equal to omega over k times b naught. What's omega over k? That's v, right? The speed, v. So we get v times b naught. But what's v? At what speed is this wave traveling? At this speed, yeah, the speed of light. So yeah, sorry, I didn't realize I was over time. Let's pause here and we continue with this next.